Welcome back again after the tea break. We are now at the 8th lecture, I think, in the course. The topic is actuator stroke amplification. So we are after the tea break. We'll have lunch after this lecture, then another lecture, and then the lab. We will have a look at different actuator designs. So using the piezo-ceramic transducers together with other structural systems to increase the stroke or the displacement we can get from them. The learning goals are that you know the quantities stroke amplification factor, force reduction, then the quality criterion, and explain their significance. You know various bending actuator designs and can also classify them according to their stroke amplification and their quality criterion, so rank them against each other. You can describe the influence of the substrate or carrier or structural material of bending actuators. And you can name further configurations of stroke amplifying actuators compared to the bending actuators and also explain their operating principle. Why do we want to have stroke amplification? As we have seen, the piezo-ceramics have very small deformations, 0.1%. And this is often not enough for our technical use cases. And therefore, we design systems which amplify the stroke or the displacement. And we have two criteria, or three in total. The stroke amplification factor, it's theta V, which is the deflection of the amplifying system, so of the overall system without load, over the deflection of the piezo monolith. So we compare the stroke of the system with just the stroke of the piezo monolith. And the same is for the force reduction. In this case, we compare the blocking force of the system to the blocking force of the piezo-ceramic piezo monolith. And then we have also a quality criterion, which is defined by the product of stroke amplification times force reduction. We will come to that in a few slides. The main type of stroke amplification systems are bending actuators. We already had bending actuators with polymer-based functional materials. We can have a monomorph, which is a composite of a passive and an active layer. We have a structural material and an active layer or a functional material on top, field in thickness direction. And we use D31 effect, and then we can bend this actuator when we extend the transducer. And then blocking force means the force to push up again, for example, the tip of the bending actuator. So we activate the layer, and it will bend with a higher stroke than the piezo monolith. And if we push it back again to zero displacement at the tip, this would the force we need for this would define then the blocking force. Next configuration is the bimorph. It's a two-layer composite of active layers, so we don't have a structural or carrier layer. We just have two layers of functional materials on top of each other. And if we then extend in this direction and contract in this direction, we can also have high bending. And the trimorph is a three-layer composite of two active layers with a structural layer in between. Here the monomorph again with a larger picture, but since we have introduced it on the last slide, we will skip that. But we can have a look at again a simple model for the calculation of the stroke amplification. If we use Bernoulli or Euler-Bernoulli assumptions, then for beam bending we have this Euler-Bernoulli ODE. In our case, no, sorry, I mixed it up. It's in our case YE times the fourth derivative of W. W is the transverse deflection. So for example, W at the position x equals L would be the deflection here. Then the first derivative of W is the slope or the rotation of the beam. And if we put it into this equation, then we have an equation for the displacement, for the axial displacement, which comes from the axial elongation times the x coordinate, which goes in this direction, plus the axial displacement due to the bending, which is z coordinate, so distance from the neutral axis times the slope. And we can also define our strain from the actuator layer, so from the active layer, small signal behavior again. Here we have the strain from the mechanical part and strain from the piezoelectric part again, as we have seen in the last lectures. And this we could also write as the partial derivative of UA, so the displacement of the actuator layer derived with respect to x, and this part here also as a derivative, and then we are back again here. And together this, if we transform it to sigma A, we have the normal stress of the actuator layer, which consists of the normal stress due to the axial strain, then the normal stress from the normal stress from the bending, from the curvature. Now it's the second derivative, so the curvature of the bending line, and here we have again the piezoelectric part. We can do the same for the substrate or structural layer. And then we get this equation, which is the Young's modulus of the structural layer times the actual elongation, and then again the stress from the elongation due to the bending. But we don't have the piezoelectric part compared to the slide before, because we have a passive layer and no piezoelectric effect. So we now have two equations for the stresses, one for the actuator layer and one for the substrate layer. And if we don't have an external force, or at first we can sum up these stresses and integrate them over the height of the different layers, so height of the structural layer and height of the actuator layer, and the same for the moments, but then we have to multiply it with the z coordinate for the lever to get the moment, and integrate it for the cross section. Then we have an equation for the normal forces. If we then integrate it, so we maybe go one slide back. I have to have the cursor to be able to move between slides. So if we integrate this, then we get these equations, and then we can transform it to the curvature of the whole monomorph, and we can see that the curvature of the monomorph is dependent on the Young's modulus of the two materials, but also on the geometry. So HA, the thickness of the actuator layer, and also the thickness of the structural layer, and also, of course, of the piezoelectric constant and the electric field. We can then integrate it 2 times using the boundary conditions we know at this point, which is x equals 0 with a clamped boundary condition or a fixed end, that the deflection should be 0, so we have no deflection here, and also the slope at this point is 0, so we can also use this as a boundary condition. And then after integration, we have this equation for the deflection independence of the x coordinate of the whole monomorph, and then we can look at the specific case x at the position x equals L. So this is here at the end. So this is W L, for example, here in the picture. And now we have an equation for the deflection of the monomorph, which looks rather complex, but it is dependent on the piezoelectric effect, and this thing here we can say is the stroke amplification factor, and this is what we call theta V in the beginning. So now we have from this Euler-Bernoulli ODE derived for our monomorph an equation to calculate the stroke amplification. I'm not sure if stroke is really the right word in English. A stroke means so the displacement of the system. In a combustion engine, you have the stroke of the cylinders going up and down, and this is so the stroke, the displacement the whole system can make. Yeah, peak to peak, yes. Yeah. So we can simplify this when we summarize the stroke amplification for the monomorph. Therefore, we have here the capital M for monomorph, and here also capital M. We could also say that the electric field times the thickness of the. And then what we now can do is we can introduce some ratios, like the ratio we had in the beginning with the different or similar, like this, the stiffness ratio with the spring stiffnesses in the work diagram, where we said that a ratio of 1 leads to structural conformity. And if we do this and use these ratios in the stroke amplification factor, then we get this equation where we don't have to put actual numbers for Young's modulus, but we can look at different ratios between the Young's modulus. And still the thickness ratios, or we have here some, actually always to click that I can change the slides. So we took this equation as the stroke amplification and replaced Young's modulus and most of the thickness values with these ratios, and with that we have this equation for the stroke amplification. And what we now can do is we can look at the different ratios using the stroke amplification and plot it. So we have here on this axis, on the z-axis, we have the stroke amplification. Here is alpha HA, well, alpha HA, which is HA divided by HS, and here is the ratio of the thicknesses, or of the Young's modulus. And what we can see is that at this point we have the maximum stroke amplification, which is around a ratio of 1 for the thicknesses, so same thickness of the structure layer and the actuator layer, and it gets higher in this direction. So again, a high modulus of the actuator compared to the structure gives us a high stroke amplification. Of course, this is again a simplified model, just with Euler-Bernoulli assumptions, but to get an impression. This is for a bit more complex system, also a way to look on structural conformity. If you want to achieve high values for the stroke amplification, you have to look at the Young's modulus and also on the dimensions of the different layers. Of course, we can also do this for the trimorph. I will go through it a bit quicker. We have here the Euler-Bernoulli ODE again, and now with the actuator moment, because now we don't just have an elongation of one layer, but one is extends and one contracts, so we can apply a moment. And in the end, we can have a same equation or a similar equation than before for the deflection curve of the trimorph, now indicated with a T. And it's again dependent on the Young's moduli and also the heights of the different layers. And this, like we've done before, we can then isolate or replace the electric field or electric field times the thickness of the layer with the voltage, and then have again this part here as, well, it's not totally this part, but similar. Here is an HA, so one L is in and one HA, but we again can derive an equation here for stroke amplification of the trimorph, and then same plot as before. Here is the ratio of the thicknesses, here's the ratio of the Young's moduli, and here's the stroke amplification for the trimorph. Here's the top of the curve, at least for the limits we set, and for this, in this case, the ratio here is a bit lower maybe than 1. Can have a look at the definition of the ratios again. If it's smaller than 1, this means the structural layer is thicker than the actuator layer. So the distance from the neutral axis is larger, and therefore we can bend it more easily. And also a higher stiffness of the actuator leads to higher stroke amplification. And we excluded here the bimorph. The bimorph would be when the structural layer is 0, then you just have the actuating layers. So if we compare the stroke amplification of the monomorph and the trimorph with respect to the ratio of the thicknesses of the actuator layer and the structural layer, we can see that we can achieve far higher stroke amplifications than with the monomorph. So the trimorph has higher amplification than the monomorph, and we assume that we use carbon fiber reinforced plastics. So a ratio of alpha epsilon of 0.5, and we assume a layer thickness of 0.2 millimeters of the structural layer. And if we have an if alpha HA gets to 0, then we are here at this point. So in this case, I think the ratios are the other way around. Let's have a look a few slides back. Yeah, so in this definition, we have HA here over HS over HA, and therefore, if this gets 0, then HS would be also 0 for the trimorph. So this is the special case of the bimorph then. So here is the bimorph, which is a special different thicknesses, and we can see that again the trimorph is performing better than the monomorph. So if we take into account the stroke amplification as well as the force reduction in the quality criterion, so highest Young's modulus has the highest quality criterion, and aluminium with the lowest modulus the lowest, and for the trimorph it's the other way around. So these are the bending actuators. We looked at monomorph and trimorph, and now we go over to other actuator designs. One is an elliptical configuration, and for this we have an piezo stack actuator here in the middle, which can extend and contract in this direction, and this would deform this shell or clamped shell around made by metal, and then we get the amplified stroke in this direction. And we assume that the circumference, which is L here, so the length around this ellipse is constant, and then we can, from this we can have an equation or formulate an equation for the rate of change of the height, which is A or 2A, so this would be the height A, and this here is the length B, so we can have the partial derivative of the change of the height with respect to the length, having this equation, and this can then again be used to formulate an equation for the stroke amplification. So we introduce a ratio again next alpha S in this case, which is A over B, and with this we have an equation again for stroke amplification of this elliptical design, where this alpha S is in, and we say alpha S is in the limits 1/9 and far smaller than 1. And if we plot then the stroke amplification over the ellipse aspect ratio alpha S, then we can see for small ratios we have the highest stroke amplification, which means that A is small compared to B. So if we have really a slender ellipse, so less height and long length, then we get far. So this would be the beam and this would be the lever. So we say it's an rectangular shape for simplification. And then we can introduce again stiffness ratios, have our well-known equation for the electromechanical coupling for small strain behavior. And we have the actuator force, which is the force the piezo stack actuator can bring up, and in this direction we would have the blocking force again if we actuate the Muni actuator to its maximum stroke and then push it back to its initial configuration, and the force we need would then be the blocking force in this case. So again, using the Euler-Bernoulli differential equation, we finally get to the equation for the maximum deflection. So here at the maximum deflection, we assume like the free displacement that the blocking force is 0. And we have this equation for the W max, and we can also calculate the limited actuator displacement because it's not really a free displacement in this Muni configuration, even if it's in the direction we want to use the stroke, not clamped or fixed. So we have no force in this direction due to the casing around. It's restricted, a restricted displacement of the stack actuator, and this is integrated in this equation from the model. But it's not necessary for the exam. I think if you like, you can go through the slides afterwards if they are provided to look at the model itself. We then again have a stroke amplification factor for the Muni actor. So M stands now for Muni. And for this, we have the maximum or the free displacement of the stack actuator, which is the height times the piezoelectric constant times the field. So this would be in our easy, or in the simpler case, U0 of the stack actuator, and we compare it with the maximum displacement the Muni actor does in the other direction, so perpendicular to it, to get the stroke amplification factor. And we can again introduce ratios of the spring stiffnesses and also on the, now I'm missing the word, in Germany it's the Flächenträgheitsmoment, so it's the bending moment I, E times I. What is the word for the, I have to look it up. So this is the bending stiffness, E times I. E is the Young's modulus and I is the moment of inertia is the word I was missing, yes. And in German it's Flächenträgheitsmoment. I was missing the word. So ratio of the moment of inertias and ratio of the stiffnesses. And then if we have a look again at the stroke amplification, we can see here that with higher stiffness of the structure compared to the stiffness of the actuator, we get higher stroke amplification in this case. Go out and have also a larger stroke than just a simple piezoceramic actuator. And here the amplification depends on the number. Then another Another concept would be the inch-worm, which is a linear drive made from piezo actuators. We may go through it. So the first step, or in the first place, this rod here in the middle is not clamped at all. In the second phase, so we have three areas, this one, so two clamps, which will actuate in this direction, and then we have in the middle actuators actuating in this direction. Then in the second step, it's clamped here, and in the third step, then we use this actuator to elongate, and then we clamp also on the other side here, and then we loosen the clamp on the left side, and we can contract the actuator in the middle again, and then we start again here, and with this we have a linear drive made by piezo actuators. The maximum actuation force is not high, 20 newtons, but we can have strokes depending on the rod length of up to 200 millimeters, and it has really a high resolution of 4 micrometers for the displacement, and speeds up to 2 millimeters per second. And let me quickly go through an animation. If I missed to load it before, but we can look it up directly here. So it's the same inch-worm. Here a second. Inch-worm drive, which is this one I was looking for. Here you can see the principle with an animation. And with this you can use the different actuators to have a linear drive and push a rod through it. If we compare these in terms of stroke amplification, force reduction, and quality criterion, we have for the monolithic actuator, or set the monolithic actuator as a reference, so we have a stroke amplification of 1, force reduction of 1, and therefore also quality criterion of 1. And for the Muni actuator, we have a stroke amplification of 4 to 15, but also low values for the force reduction, meaning high force reduction, because this is this theta p would be multiplied with the blocking force, and therefore low values here give low blocking forces for the system, and therefore we have quite low quality criteria. The bimorph has a better quality criterion, also higher amplification factors, so the force reduction is maybe also high, but in the same range than before, but we have a higher stroke amplification, so the quality criterion is also higher, and the telescope is even higher because the force reduction is not that high in the system, so we get high forces and an average stroke amplification. The stack actuator is also mentioned here. It has a force reduction. I think it is due to the interlayers you have. So you have to have adhesives in between, and the electrodes and so on. And therefore the blocking force is lower than compared to a monolithic with the same outer dimensions. And now we, at the end, we come to example applications. I looked up one example application. It's also from the retired professor who also gave this course together with some colleagues from German Aerospace Center from our institute. So it's an application on an aircraft flap here we have the trailing edge of an aircraft wing, and it uses a Coanda flap. It is a highly deflected flap, and if you only have a passive system, then the flow would not stick to the flap till the end of the flap. It would detach earlier. And what you can do is you can have a system which blows out air here, and with this new energy, new impulse in the boundary layer, it would stick longer to the flap, and therefore you can increase lift with this Coanda flap. And the idea was to have here a system of lips where you can control the airflow with. So a sensor was integrated here, measuring if the airflow is still attached to the surface or if it's detached. And if it's detached, then this lip would open and blow air here out, and therefore then the airflow hopefully attaches again. And with this, you have a high lift device producing high lift coefficients. And yeah, I cited this paper 4 where it was published in. There were 2 stroke amplification systems or concepts for these lips under investigation and compared. These are the 2 lip systems. So this is more or less a trimorph. We have a piezoceramic patch actuator on top and bottom and a structural layer in the middle. And the other design was a piezoceramic stack actuator with a compliant lever. Here is a structural hinge, and if you extend the stack actuator, the lip would move down, so you have also the same effect than with the bending actuator. So 2 different designs of stroke amplification for this Coanda flap applications, which were basically possible. And they found out that they decided to use this approach. It looked like this, the real design of this lip actuation. So you have the lip here. You have a sleeve with a piezo stack inside, which is then screwed in here. So here's the piezo stack pushing against the lip with a compliant hinge, and then the lip would move up and downwards. And in the wind tunnel model for testing, we had a row of these lips, so you could have differential control of blowing out the air over this bandwidth. And yeah, it was also tested in a wind tunnel, I think in the German-Dutch wind tunnel, which is also located at German Aerospace Center in Braunschweig. Yeah, just to, not going too much into detail, but just to show you a real application case for aircraft structures using this stroke amplification systems. If you want to learn more about this, then I would refer you to this publication 4. It's, I think, 5 years old, published in 2020. And with this, I would conclude this lecture. We have defined a stroke amplification factor, theta B, which is the displacement of the system or the stroke of the system compared to the free displacement or free stroke of the piezo stack, or not the piezo stack, the piezo monolith. We have a force reduction, which compares the force of the system with the force of the piezo monolith. So the force of the system is always lower if we have a higher stroke. Therefore, this number, if this number is small, then we have a high force reduction, and their product is a quality criterion to take into account both the amplification and the force reduction. Bending actuators, which are based on planar functional or piezo elements, like we've seen in the lecture before, can be used or are based on these actuators using the D31 effect, And from these bending actuators, the trimorphs achieve higher stroke amplification and also better quality or higher quality criteria. In terms of structural conformity, the substrate or the structural properties of the carrier layer matter, so thickness and Young's modulus affect the performance, and for monomorph actuators, the higher Young's modulus is beneficial for the stroke amplification, which is not the case for the trimorphs. And we had a look at some alternative concepts like the elliptical and the rhombic amplifiers, just models of these, and realized Muni actuator with a flexural cap, and had a quick or brief look also on telescopic actuators. And with this, I'm at the end of this lecture. I'm open for questions, and otherwise now we will have the lunch break. Yeah. Mm-hmm. Yeah. 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 So to turn around the sign, I think in a small range you can also actuate it